Our next speaker is Yaoting Lin, and he's going to talk about cryptography in the common hash state model, feasibility results, and separations. Take it away.
Okay, thanks for the introduction. So I'm going to talk about cryptography in the common hash state model, where we show some feasibility results and separations. This is a joint work with Prabhanjan and Aditya, who is also in the audience. So I'll begin by an introduction. So as we know, most crypto primitives cannot be unconditionally secure in the plain model. So to bypass these impossibilities, models with a trusted setup have been introduced. And one example is the common reference string model, where the setup outputs a reference string to each party. And it has many applications in NISIC, MPC, etc. In another example is the common random string model, where the setup outputs a random string. And because the random string has no structure, so this model is easier to instantiate and is more desirable than the common reference string model. So a question is, could quantum be useful? Can we leverage quantum powers in these two models? And surprisingly, a recent work by Morime, Nihoram, and Yamakawa showed that statistically hiding and statistically binding quantum commitments exist in the so-called common reference quantum state model. So I'm not going to define it, but it's basically a quantum analog of the common reference string model. And such a scheme is impossible in a plain model or even in the common reference string model. In our work, we introduce a new model called the common hash state model, or CHS model. And it's a quantum analog of the quantum random string model, of the common random string model. So in the CHS model, the setup outputs polynomial copies of a hard random state to each party, including the adversary. We need polynomial copies because of the no-cloning theorem. And there's another independent and concurrent work by Chen, Koladandjarian, and Satath, which also introduced the same model. So why do we study the CHS model? So first of all, it allows us to bypass impossibilities in the plain model. So as we will see later, some primitives that require computational assumptions could be statistically secure in the CHS model. And next, it provides a modular approach for designing crypto primitives. So suppose we have some construction in the CHS model. Then we can instantiate the common hash state by state designs or pseudo-random states in the plain model. And furthermore, we can use CHS model to prove black box separations between quantum primitives. And before I dive into our results, I will give you a brief background on quantum pseudo-random primitives. So as you already saw in the previous talks, a PRS was defined by Giulio and Song, and is a quantum analog of a PRG. And the output is computationally indistinguishable from hash state, even the adversary holds many copies. And just like a classical PRG, statistically secure and stretched PRS is impossible in the plain model. And we also have pseudo-random function-like state, or PRFS, generator. And it was defined by Anant, Chen, and Yuan. It's a quantum analog of PRF, and is computationally indistinguishable from Oracle that outputs an IID hash state psi x on input x. So here's our result. So we construct bounded query statistically secure PRFS in the CHS model. And importantly, is under the parameter regime that is impossible to achieve in the plain model. In particular, this PRFS is secure against the order n over log n to the power of 1 plus epsilon number of queries in the CHS model. And if we instantiate the common hash state with a PRS, then it gives the first construction of PRFS with super logarithmic input length from PRS in the plain model. And combining with known results, it implies bounded copy statistically secure stretch PRS and statistically hiding statistically binding quantum commitments in the CHS model. And compared to the work by Chen et al., not only our results are stronger, but our proof is simpler and more elementary. And on the other hand, we also show that our construction is optimal because we break a class of PRS construction using order n over log n copies of the PRS state. While the other work shows a more general attack that breaks every construction, but using slightly more copies. And one might wonder if we can have stronger primitive in this model. But unfortunately, we show impossibilities of statistically secure quantum computation, classical communication, or QCCC, key agreement and commitment. So QCCC refers to a model in which each party performs local quantum computation and classical communication. And we also show the black box separations between PRFS with super logarithmic output and QCCC key agreement and commitment. And to prove the last two results, our main technical tool is what we called the LOCC hard indistinguishability. So what does this mean? Consider the following question. Can two communicating parties with high probability distinguish IID versus the same hard states? So more precisely, on the left, the challenger sends T copies of psi A to Alice and T copies of psi B to Bob, where psi A and psi B are two independent hard states. And on the right, the challenger sends T copies of the same state, the same hard state to Alice and Bob. And if they can do quantum communication, then Alice can send one copy of her state to Bob, and then Bob can do a swap test. So they can easily distinguish. But if they are only allowed to do classical communication and shares no entanglement, even if they are computationally unbounded, we show that their distinguishing advantage is at most order t squared over 2 to the n, where n is the length of the hard state. And we, in fact, prove something stronger. This bound holds for positive partial transpose operators, which is strictly more general than the LOCC operators. And also, this bound is tight because we construct a distinguisher that achieve this bound. Yeah, and although we construct PRFS, for simplicity, I will tell you our PRS construction, which is a special case. Also, is it old version? Yeah, so our construction is extremely simple. So on a key K and one copy of the common hard state psi, the PRS state is defined to be Z to the K acting on psi, where Z to the K is the tensor product of a poly Z operator, and is efficient and has stretch. And for security, I don't have time to talk about the details, but we use the tools in the symmetric subspace and some elementary combinatorial arguments. And this construction turns out to work for psi of any length greater than or equal to the key length. And let's move to the negative result, which is the impossibility of interactive QCC primitives in the CHS model. So we have a very simple framework for proving impossibilities. Suppose we want to show the impossibility of some statistically secure QCC protocol, for example, key agreements or commitments. Then toward contradiction, let's assume they exist. Then we can define a new protocol in the plane model as follows. We can replace the common hard state psi with two independent hard states, psi A and psi B. And because now they're independent, so Alice and Bob can sample them by themselves. And by LOCC hard indistinguishability, doing this won't hurt the completeness and security too much. So the new protocol in the plane model remains correct and statistically secure. But this is a contradiction. And we can extend the idea to prove the separation between interactive QCC primitive with PRFS with super logarithmic output length. So if the PRFS or PRS has the output length of order log n, then they in fact imply a QCCC commitment. So our separation actually complement this positive result. So in our work, the idea is to consider a stronger variant of the CHS model that trivially implies PRFS. So now, the setup instead prepares a set of IID hard states indexed by a key k and input x. So whenever the party queries on kx, you will get one copy of the state psi kx. So this gives a natural output for the PRFS. And we can use the same idea and LOCC hard indistinguishability to rule out QCCC key agreement and the commitment relative to these hard states. Yeah, and here's the summary. So we define the common hard state model, which is the quantum analog of the common random string model. And we show some statistically secure primitive exist in this model, which are impossible in the plain model. And we also show the black box separations between interactive QCCC primitive and the PRFS with super logarithmic output length. And there are some open questions and the follow-up works. So we can consider a stronger model called quantum hard random oracle model, in which each party has access to a hard unitary oracle. And it's interesting to study the feasibilities and the limitations of this model. And another interesting open question is whether LOCC hard indistinguishability holds even in these oracle settings. And that's all of my talk. Thanks.
Thank you. We have a few minutes for questions.
So this separation, is it with respect to like an isometry oracle or a unitary oracle?
Oh, so that's a good point. So it's an isometry oracle.
Okay, do you know when they send it to a unitary oracle?
So the work by Chen, Coladangelo, and Satov, their paper actually achieve separations with respect to a unitary oracle. Yeah.